I feel like I've kind of beat you over the head with electrophilic addition reactions, but there are other aromatic reactions that we need to look at. So let's just dive into them. Okay, the first type of reaction that we're going to look at is nucleophilic aromatic substitution. We've been talking about electrophilic aromatic substitution so far, but there are some nucleophilic substitutions. These are not common, and they usually only occur if you have electron withdrawing groups on them. And the leaving group has to be either ortho or para to the electron withdrawing group. What you have is the nucleophile adds to where the leaving group is. The anion that forms is stabilized through resonance with the nitro group, and then the leaving group leaves. It's not SN2, not SN1, it's just nucleophilic aromatic substitution. But these are not common, and I'm not going to emphasize these reactions. Here's an example. For instance, you can have hydroxide come in, and it adds to where the chlorine is, and the negative charge is stabilized then by the nitro group. And then what happens is the chlorine leaves and aromaticity is reestablished. And this is typically how they go. When I first gave you the formation of benzene sulfonic acid, I said if you treated that with hydroxide at high temperatures, the benzene sulfonic acid would be substituted with the hydroxide to form phenol. And it is in a reaction similar to this that occurs. So here's stabilization of the negative charge. It is through the pi system and the electronegative atom of oxygen. You can see through resonance how it is stabilizing this. Okay, another reaction that is quite useful is that carbon chains can be oxidized down to the carboxylic acid functional group. So this can be a long chain, 4 carbons long or even longer. As long as this carbon has at least one hydrogen bound to it, potassium permanganate is going to cleave all those other carbons off and oxidize this down to the carboxylic acid. So what is it you need to look for? A carbon chain and at least one hydrogen on the carbon that's adjacent to the ring. So what happens in these reactions? We have styrene and we have T-butylbenzene. What happens when we treat them with potassium permanganate? Well, if I look at this carbon, you can see it is going to have one hydrogen attached to it. So it can be oxidized down to the carboxylic acid, and we produce benzoic acid. However, T-butylbenzene has no hydrogen here, so there is no reaction. You might remember this first reaction from last semester. We called it allylic bromination. And the position that is adjacent to a double bond is called the allylic position. And when we treat it with N-bromosuccinimide and light or heat, it decomposes and produces a tiny amount of bromine free radicals. And those bromine free radicals then will brominate this ring in that position because a free radical is stabilized by the pi system. Well, we see exactly the same thing with the benzene ring. It stabilizes the free radical in the position right here. And whether this is a methyl or an ethyl or a huge long chain, where is bromination going to occur? Right there in the position, in the benzyl position, adjacent to the benzene ring. Okay, go ahead and try these reactions. If I treat this, this would be methyl benzoic acid with N-bromosuccinimide and light, what happens? Likewise, if I treat ethylmethylbenzene, or I guess you could call it meta-ethyltoluene, with iron 3 bromide and bromine, what do I get as a reagent? Well, on this first one, this is bromination that will occur in an activated position, and the carbon adjacent to the ring right here is activated toward bromination. So what will be the product? We will get bromination on that carbon. Whereas here, what happens? We're not going to have bromination occur because we have the iron 3 chloride, and if we just use one equivalent and there's no light or heat to cause the bromine to make free radicals, all we're going to have is bromination of the ring. So here we see that both the ortho and para positions, these are ortho and para to both of these, and this is ortho to both, but it's too crowded. So you can have bromination occur here or here. This group is bulkier, so this position is less likely to have bromination occur. The most likely position for bromination to occur is right here, although there would be some there. Aromatic compounds can be reduced. If we use hydrogen and palladium, we can reduce double bonds at 1 atmosphere, but we're not going to be reducing a benzene ring. It requires a lot of pressure, like 3 atmospheres, in order to reduce that aromatic ring down to a cyclohexane ring. This is good because it gives us selectivity. So if we want to just reduce a double bond, we'll use hydrogen and palladium. If we increase the activity of the metal catalyst to something like rhodium or platinum, you actually will reduce the aromatic ring as well as a double bond, and you only will have to use 1 atmosphere or slightly more, maybe a longer reaction time. We have seen that carbonyls can be reduced with lithium aluminum hydride and sodium borohydride, and it takes it down to alcohols. Nitro groups can be reduced down to amines with sodium borohydride and lithium aluminum hydride. Just lithium aluminum hydride. But when you have nitro groups, and carbonyls also can undergo some other reductions. When the carbonyl is adjacent to an aromatic ring, it is activated to reduction down to a methylene group. And you can do that both with hydrogenation or with another reagent that I'll give you in a little bit. Nitro groups also can be reduced to amino groups by hydrogenation. And we can actually reduce them with another type of reducing agent like iron and hydrochloric acid, or tin and hydrochloric acid. This way is, in order to do a better type of alkylation of a ring than using the Friedel-Crafts alkylation, which has the problem of multiple alkylations, we can actually put an acyl group on the benzene ring that's a chain with a carbonyl adjacent to the ring, and then we can reduce that down to a methylene group with hydrogenation, and it avoids the multiple alkylations that you get with the Friedel-Crafts alkylation. Instead, you're doing a Friedel-Crafts acylation. You can put an amino group on a benzene ring by putting a nitro group on it and then reducing it down to an amino group. Let's look at this. Nitro groups can be reduced by hydrogenation or by tin or iron and acid, and you would follow with a basic wash because you're making an amine and the acid would tie it up, and you release it by washing with base. Hydrogenation, though, is non-selective, and you're going to reduce aryl ketones down to the methylene group, and if there's any double bonds anywhere, you're going to reduce that alkene to an alkane. Acid and tin is selective and will not reduce an aryl ketone or an alkene. So when you just want to reduce the nitro group and not other functional groups like the carbonyl next to a benzene ring or the alkene, you use acid and tin, or iron works also. Okay, here's some examples. If I use hydrogen over palladium, well, you're getting just reduction of the double bond. But if I use hydrogen over rhodium, not only do I reduce the double bond, but I reduce the benzene ring. Why? Because rhodium is a much stronger, more active catalyst than palladium. Okay, here's some examples, more examples. We have hydrogen over palladium. Notice it's not reducing this ring, but it does reduce the aryl ketone down to a methylene group. If I treat this metanitro acetophenone, notice both the ketone adjacent to the benzene ring and the nitro group are reduced down to an amino group and just a methylene. But if I treat this with tin and hydrochloric acid, I reduce only the nitro group. The ketone is unaffected. So what is the outcome of treating nitrobenzene with hydrogen over palladium? Well, what you get is no reduction of the benzene ring and reduction of the nitro group to the amino group. So we get aniline. What is another way to reduce nitrobenzene to aniline? Well, if we use tin and hydrochloric acid followed by base to deprotonate the aniline, it will work. Which conditions also reduce a carbonyl adjacent to the benzene ring? Hydrogen over palladium. So where is free radical bromination most likely to occur on this compound? Well, if you look over here, you can see this is tertiary and that's secondary. And you might have said, well, tertiary free radicals are more stable, so it's going to occur there. But remember, this carbon is adjacent to a benzene ring, and that activates this position. And so this is the most stable free radical in this position. So when free radical bromination occurs, where does it occur? Right there on that carbon. What conditions would you use to do free radical bromination? N-bromosuccinimide light. Why do we use those? Because NBS gives us a low concentration of bromine that gives the selectivity that we want. So what conditions would you use to add bromine to the aromatic ring and not in that position? You would use bromine and iron-3 bromide, and these conditions don't give you free radicals, so you instead have electrophilic bromination.